So there's one type of question on the worksheet that's due on Thursday that we haven't seen yet, and that's rational equations. So technically this is a type of problem you normally see towards the end of Math 46. So it's not part of our 96 curriculum, but it is important that you're able to tackle it because there's a lot of rational equations that come up and rational functions and rational expressions in both Math 104 and 116. So a rational equation looks like what you see right here. Remember, something that is rational means that there's a polynomial divided by another polynomial. And when we're in equation land, really what it means to us is that our variable is trapped in a denominator. So in many ways, it's similar to previous problems where our variable was inside of a square root. Our variable was squared, right? We need to figure out how do we deal with that. And generally speaking, there's two different methods that we can use to handle this. Method one, you could set up equivalent fractions. This tends to not be the best way to go, but what I mean by this is there's no reason I can't actually add the two fractions on the left-hand side here, right? So I could go ahead and multiply that first fraction by 2 over 2, so that now we have common denominators, and I can add those together. So now I'm looking for something where these two fractions would be equivalent to one another, right? And this is where you could do cross multiplying. Most teachers consider cross multiplying sort of a bad thing to do, but you could do that where you have your, okay, if these things are equivalent, that means 7x has to equal 6, and that means x must be 6 over 7. And if you checked your work on this, back in this part, because I feel pretty good about our adding of fractions, we're saying that 1 divided by 6 over 7, which is 1 times 7 over 6, is equal to 7 over 6. So it works out. But the one thing I don't like about this method is that this method requires that we do a lot of fraction math and that we feel comfortable with manipulating these rational expressions, which is something we haven't covered because it was technically 46 stuff. So instead, what I like to do as a better method, in my opinion, is to treat these like we would a regular equation and clear fractions. So we're not going to do that first method, though it is legitimate and you could think of it that way. I'm going to clear my fractions. So remember, if we had something that looked like 3 over 5 minus 2 over 3 is equal to x over 6, this is hideous writing, but if we multiplied both sides by our least common denominator for all of our terms, so maybe by 30, then as we multiply 30 to every term, 30 divides by 5, so we get 6 times 3. 30 divides by 3, so we get 20, and then 5x. You can see that we can immediately get rid of our fractions. And if we need to, we can always take that sort of baby step first of rewriting this as like 90 divided by 5 minus 60 divided by 3, putting this over 1, and then carefully multiplying our numerators, and then doing the simplifying to get to here. So we can do that same thing. We just have ugly pieces here. So we have a 3, a 6, and an x in our denominators. So the least common denominator for least common multiple for 3 and 6 would be 6 itself. But we also want to get rid of this x. So I'm going to multiply both the left side and the right side by 6x. And I'll put it over 1 so I don't get confused. So if I do that, again, this time I'll take those baby steps that I did here, right? I get 6x divided by 3 plus 6 times 5 is 30x divided by 6 is equal to 6x over x. And then we can take that moment and simplify. Again, you can jump straight to this if you see it happening immediately. So first term is 2x, then we get a plus 5x is equal to, the x's cancel, we just have 6. And we can combine our like terms and divide both sides by 7. Same answer we got previously, just a different way to get there. So this is a little bit harder on the questions you have on that worksheet, so I'm going to do a slightly more difficult one, right? The ones on that worksheet look more like this. Which one do I want to do? I'm looking for one that's ugly enough, because I know the one on your worksheet is pretty ugly. Let's do this one. 5 over t minus 3 minus 30 t squared minus 9 is equal to 1. So again, we have variables, but they're in the denominators. We have two different denominators. So what you want to do in this case is you want to think about both of those denominators. It would not make sense to just multiply by both of them, because what's going to happen is we're going to end up with a t cubed, and bad things will happen. So we actually want to go back to our factoring skills. So if we factor, well, this one's as good as it gets, right? But t squared minus 9 is our difference of squares. That's t minus 3 and t plus 3. And if we rewrite this denominator for this second term as t minus 3, t plus 3, we can actually see already these two denominators have t minus 3 in common, right? So my least common denominator, that does not need a second t minus 3. Let's think back to a simpler example really quick. If I want the common denominator and say my denominators were 18 and 15, 18 is 3 times 6, 15 is 3 times 5. We have 3's in both of these, so when we multiply, we only need, our least common denominator is going to be 3 times 5 times 6. We only need 1 3 because these 3's already matched up. We don't need to multiply by something again. And kind of think about this back towards our factoring stuff. So anyways, if that t minus 3 is in common, this means for this one, our least common denominator is that t minus 3, t plus 3. And I'll show you how that works by multiplying it out. And I think that'll help a little bit too, because I'm trying to get through this a little bit fast, but we'll have extra time to talk about it in class on Monday, so that's why I'm not too worried about going quickly. So if I multiply both sides by that t minus 3, t plus 3, again, I'll move slow. I'll do that step. So the top of this one, the numerator is going to be 5 times t minus 3 times t plus 3, all over that t minus 3. Our second term, still have the 30, t minus 3, t plus 3. Move all these little numbers. We don't need them anymore. And that's all over our factored version of that denominator, t minus 3, t plus 3. This is all equal to t minus 3 times t plus 3. Just because there's no denominator on this side doesn't mean it gets multiplied, right? It's got to be fair. And then we can do some canceling. Since that's in common and they're both factors, we can go ahead and say that this is just equal to 1. So we can get rid of it. Same thing here. Both of those are fancy pants versions of the number 1. So this is going to be 5t plus 3 is minus 30 is equal to t minus 3 times t plus 3. And then we're going to have to do some distributing. Distribute here. We'll do some distribution here. Some foiling, however you want to think of that, right? So that we can clear parentheses just like we would in a normal equation. 5t plus 15 minus 30 is equal to t squared minus 9. Oh, yeah, that was just that other denominator. So 5t minus 15 is equal to t squared minus 9. And then let's think about what type of problem we're now dealing with. Now we can see we have a t squared, right? And if we have a t squared, that means we're dealing with a quadratic. And like I said, anytime we get a quadratic in Math 96 that we didn't start with a quadratic, chances are it will solve by factoring. Right? This is not necessarily true when you get to 104, 116. You might have to use a quadratic formula, but 9 times out of 10, it will factor. And in order to factor, I need to first set aside to 0. So I'm going to subtract that 5t, add the 15. So I get 0 is equal to t squared minus 5t plus 6. And then I'll think about whether or not that thing factors. Looks like it does. This is going to be t. Does it work? Does it not work? It works. Gosh, whew, got nervous for a second. I really wanted it to be like 5 and 1. That was like, that doesn't work. But -3 and a -2 multiply to a +6, and they add to a -5, which gives us two possible solutions. T is equal to 2, T is equal to 3. We do need to check these numbers out. This is just like when we had the radical problems. Because our original problem has a part where we can't plug in, like in this case, our denominator can't equal 0. There's a domain restriction. We have to check this back in our original problem. So if you look back at the original problem, which is way, way back, but I'm trying to find it. Here it was 5, t minus 3 minus 30, t squared minus 9 is equal to 1. We can already see what the bad numbers are going to be, right? It's not nearly as hard as it is to, you don't have to actually go through all of the work of checking like you would in a normal one. If you wanted to though, 5 all over 2 minus 3, if I plug in t is equal to 2, minus 30 all over 4 minus 9 is equal to 1. So 5 over -1 minus 30 over -5 is equal to 1, which gives me -5 plus 6 is equal to 1. Check. T is equal to 2 works. But here's what happens when we plug in t is equal to 3. 5 over 3 minus 3 minus 30 all over 9 minus 9 is equal to 1. So we get an undefined value minus another undefined value is somehow equal to 1. This does not work. As soon as I saw this problem, I knew t could not equal 3, and because of this one, how it factored, t could also not equal -3. So that's another way you can handle these problems, is that at the very beginning, as soon as you make your LCD, you can go ahead and say, okay, those are two values that it can't be because they're in the denominator and we can't divide by 0. So, and then you don't have to go through the whole check process. You just look and say, oh, that was one of my excluded values. T is equal to 2.